in this example, we want to look at a couple word problems. In this first one, we have a movie theater where there's a 32-foot tall screen that's located 8 feet above the ground. And we're trying to find the viewing angle for someone. So in other words, this part in blue, whose eye level is 6 feet above the ground. So what we want to look at is uh, we have two essentially right triangles here. We've got the triangle from the person's eyes to the screen to the back down to his eyes again, and we've also got this angle from the person's eyes to the bottom of the screen and back down. So uh, the book has called it theta 1 for that small angle and theta 2 for that large triangle. So if we're trying to figure out uh, what that theta is, so theta 1 is going to be related to the inverse tangent in that um, we know that tangent is opposite over adjacent. The opposite side would be this little chunk right here uh, that's below 8 feet off the ground but above 6 feet. So therefore, between the person's eyes and the bottom of the screen, the opposite side is 2, and then the adjacent side is what we're calling D, this distance from the person to this screen. Notice the viewing angle wouldn't change no matter where that person is seated. So theta 2, in much the same way, is going to be the inverse tangent of this vertical distance of the bigger triangle, the bigger right triangle. And we know that if we went from the person all the way to the top of the screen, it would be 38 feet. But we have to take into account that there is, um, let's see, we have to take into account that there's this 8-foot part that's not there, but there's that little 2-foot chunk we talked about earlier. So in all, it ends up being 32 plus that 2-foot part, which is 34. Hopefully you can see where I'm getting that number from for my bigger right triangle. And the horizontal distance is still going to be D. So now, to get this angle in the middle, I'm going to take my larger triangle's angle minus the smaller triangle's angle, and it's going to give me this viewing window. So basically, my theta, which we'll call it, is simply theta 2 minus theta 1, or in other words, we could say theta is equal to the inverse tangent of 34 over d minus the inverse tangent of 2 over d, and that's how I can model the viewing angle for this theater patron. So let's take it one step further and figure that this customer wants the greatest viewing angle possible based on that model we created. What is the uh, optimal distance that that person could sit? So let's go ahead and put this into our graphing calculator. So let me get rid of these old graphs here, and we'll put in inverse tangent of 34 over, we use the variable x, minus inverse tangent of 2 over x. And I'm going to try to zoom fit that. I'm not sure if it'll give me a good window or not. All right, so I'm actually tracing it, and I'm looking here. Obviously, our distance has to be positive, so let's not even look at the negative x values. But it looks like my peak hits right around here. So I'm going to go ahead and zoom in on that location and see what we've got. So it looks like the maximum is around let's see, still increasing ever so slightly. Yeah. So still increasing, still increasing, still increasing. Now it looks like it actually started to go down. So maybe about right here at 8 point, let's see. Looks like it's about 8.1 or 8.2 feet would be the ideal. So that's you'd want to sit 8.1 feet away from the screen, which actually seems pretty close. But that would be your maximum viewing angle. So here's a similar word problem that you can try on your own to see if you can model that difference in angles.